So exponents. When we talk about exponents, we're talking about these little numbers that go to the upper right of some other number. And what an exponent is telling us is to take the bigger number, the base, the number that the exponent's applying to, and multiply it by itself the number of times in the exponent, okay? Easier to show than to talk about with words. So 2 to the third power is 2 times 2 times 2, and we know that's right because we've got this 3 in the exponent, and that's telling us that we have 3 factors here. Okay, so just writing that more generally, if we have any number x and we raise it to the nth power, so we've got x as the base and n as the exponent. Here it says we're taking x and we're multiplying by itself as many times as n tells us, so that we end up here with n factors of x. There's some tricky things with exponents. We're kind of doing a lot with very compact notation here, but the rules that I'm going to go through are all going to make sense to you if you can just remember that when we increase the exponent, what we're doing is we're adding factors. Okay, so let's just think about what that means here. If we go from 2 to the third power to 2 to the fourth power, we add 1 to the exponent. What do? We're adding a factor of 3. Okay, so this idea that increasing the exponent means adding factors is going to be helpful. And while we're at it, let's think about the alternative. If we start with 2 to the third power and we take away 1, we end up with 2 to the second power. We're dividing. Okay, so increasing the exponent, adding factors, multiplying, decreasing the exponent, taking away factors, dividing. Those ideas are going to go together as we go through the rules here. So the rules are on a handout in kind of a simple form, not lots of talking and justification here. In this lesson, I'm going to go through the logic behind them. So rule 1 says if we have the same number x raised to the power n, multiplied by, again, that same number x raised to the power m, what we do is we add the exponents. This is x to the n plus mth power. Again, it's sometimes easier to see if we use numbers. So we've got 2 to the third power times 2 to the fifth power. And again, you sort of look, I've got the same x here as both bases. So x is 2, 2 here, but n and m are different numbers. So here n is 3 and m is 5. Well, let's just write that out in terms of what it means as multiplication. Okay, so it's 2 times 2 times 2. Here's my 2 to the third power term, multiplied by 2 times 2 times 2 times 2 times 2, barely fits, to the fifth power. So just writing that out, how many total factors of 2 do I have? Oh, look, I have 3 plus 5. Okay, 2 to the 3 plus fifth power is 2 to the 8. Okay. So that's the logic behind that rule. So that's when you multiply expressions that involve x to different powers, you can just add the exponents. What about when you divide? What if you have x to the nth power over x to the nth power? Okay, let's see how that works with our example of the 2's and the 5's here. So say we start off with 2 to the third power, and actually, you know what? I want to start off with the other. Let's start off with 2 to the fifth on top, because the second one's a little bit trickier. So let's think about 2 to the fifth power divided by 2 to the third power. And again, let's just write it out in terms of factors. 2 times 2 times 2 times 2 is my 5 factors of 2 in the numerator, and my 1, 2, 3 factors of 2 in the denominator. Okay, so what I would do to simplify that fraction is I would cancel the common factors here, because this 2 over 2 equals 1, this 2 over 2 equals 1, this equals 1. So I'm just factoring out a bunch of terms that equal 1, and that's a standard way to simplify things, especially to simplify fractions. And so I'm left with 2 squared. I'm left with 2 to the 5 minus 3 power. And so again, if you think about just what we're representing with these exponents, I'm starting with my 2 to the 5th power, my 5 factors of 2. What am I doing? I'm dividing out 3 factors of 2. I'm taking away 3 factors of 2. And that's exactly what we do when we're subtracting in the exponent here. Okay, now let's look at the other case, the one that I started to write before. What if the smaller exponent is in the top? 2 to the 3rd power divided by 2 to the 5th power. So I've got my 3 factors up here and my 5 factors down there. Okay, I'm still gonna cancel as much as I can. I'm gonna cancel these 2, I'm gonna cancel these, I'm gonna cancel these. Now, I'm still gonna be left with 2 factors of 5, but they're gonna be in the denominator. Okay, so this is 1 over 2 squared here. Okay, is that different? It's not. It's the same thing. It's the same thing if we think about this as a negative exponent. Okay, so I'm getting a little bit ahead of myself, but let me just say, if we apply the rule here, don't write out the factors, just say 2 to the 3rd divided by 2 to the 5th. Oh, the rule says that that is equal to 2 to the 3 minus 5th, 3 minus 5 power. That's equal to 2 to the negative 2 power. Okay, and that's what we're going to say. We're going to say it's like starting with 1 and taking away 2 factors of 2, even though you don't have them. All right. Let me finish just the punchline of this rule. So I've gone through this example with the 2's raised to the power of 5 and 3. The overall rule is anytime you have x to the n power divided by x to the mth power, you just subtract the exponents. So we've got a rule for multiplying the same base raised to different powers, add the exponents. Dividing the same base by different exponents, subtract the exponents. And the rule for dividing works whether you have more factors in the numerator or more factors in the denominator. But if you end up with more factors in the denominator, if you've kind of like taken away more powers of 2 than you started with in the numerator, you end up with a negative exponent. And that actually gets us to our next rule, which basically just says that's what we mean by negative exponents. Okay, so continuing our rules here, number 3 says that 1 over the power x to the n is x to the negative n. Just looking back, that's what we were writing here. Okay. This is the same as that. And again, the idea is when you are dividing a number 1, or it could be anything else up here in the numerator, by powers of x, it's taking away factors of x. Okay. So another rule that's, go back to my rules color, which is black. Another rule that's got this almost definitional-like aspect to it. Like you could think of this as what it means to have a negative exponent. Means that the factors are in the denominator. We can also think of the definition of 0 power, defining power 0. Okay, what does that mean? I have x, and I take it to the power 0. I don't really have x. I don't have any factors of x. What does that mean? What does it mean that I have? It means I have 1. Okay, this is the convention. Okay? That any number raised to the power 0 is 1, except when x equals 0. Okay. We can take any number except 0, raise it to the power 0, and we're going to get 1, and that's going to work out really nicely for a lot of the algebra that we want to do. But if we start with 0, we can't raise it to the power 0. Okay, 0 to the 0 power is undefined. Don't use, stay away. If I could draw a skull and crossbones, I would do something about that. Okay, so this is not defined, but any other number is fine. Okay, so 2 to the 0 power equals 1, 50 to the 0 power equals 1, -7 to the 0 power equals 1, always equals 1. Another point that I want to make, just because you might be wondering, back to this weird thing with 0, 0 to the first power equals 0, 0 to the fifth power equals 0, 0 to the seventh power equals 0. You can take 0 to any positive power, that's fine, okay? You can't take 0 to the power 0, because I just said, can't do it, doesn't make sense, it's undefined. And we also can't take 0 to a negative power, because that would be putting it in the denominator, okay? So 0 to the power n is fine as long as n is strictly greater than 0. Okay, our remaining rules are more straightforward. I'm kind of putting them in here for completeness. They're not things that tend to give people trouble, but let's just get them down here quickly anyway. So we're now at rule 5 here. If you start with x to the nth power and raise that to x to the mth power, okay, what you get now is x to the n times m power. Okay, so when you're multiplying exponents of x, you add the exponent, but when you take a power of x and raise it to a higher power, that's when you multiply exponents. And again, that's easier to see if we put in numbers here. If we start with 2 squared and raise that to the power 3, just writing that out, what do we have? Well, we have 2 times 2 times 2 times 2 times 2 times 2. Here's our third power is that we have 1, 2, 3 things in parentheses, and each of the thing in parentheses is 2 factors of 2. Okay, great. How many total factors of 2 do we have? We have 2 times 3, 2 to the 6th power. Okay, so nothing particularly mysterious there. Another kind of definitional rule is, we'll call this the definition of fractional powers. Okay. So if we write something like 4 to the power 1/2 there, what we are writing is the same thing as the square root of 4. That's the same thing as the square root. So we're saying what number, if we square it, would get 4. And so that's, it kind of follows from rule 5, because if we have 4 to the 1/2 power and we square it, applying rule 5 says that our n is 1/2 and our m is 2. And so what we get is 4 to the 1/2 times 2 power, following the rule that we just went over, 4 to the first power, well, 4, 1 factor of 4. So square roots are the most common fractional power that we work with, but you can have higher order roots. So for example, if you want to have 8 to the 1/3 power, what that's asking is what number cubed gives you 8? Well, there is a number, and that is 2. Okay, and that is because 2 cubed equals 8. One last thing on the square roots here, and on any kind of even powered root. So the square root of 4 is also 2, right? 2 squared equals 4. And when you just write 4 to the 1/2 power, the assumption is you're indicating the positive square root. A lot of the time, if we're just interested in what numbers, if you square them, will give you 4, you might want to remember that that -2 also is squared will give you 4. But the standard, when we just write it without indicating that it's either the positive or the negative, the standard is to focus on the positive one. Okay, one last rule. Yeah. All of the rules that we've gone through so far have involved just a single base. It's been x, maybe raised to 2 different powers, n and m, or n and m up there in the exponents doing different things. What if, for our final rule, so we're continuing the rules, what if we have 2 different bases? Okay, so we have x times y, and that whole thing is being raised to the nth power. Okay, so a single exponent, 2 different bases. This is just the associative rule of multiplication. It says that we can, when we're multiplying a whole bunch of things together, we can group them any way we want. Okay, so one thing we can do is we can multiply x and y together and raise it to the nth power, or if we'd rather, raise x to the nth power and multiply it by y to the nth power. Okay, so this is kind of a straightforward distributive property. And again, let's just check it out with numbers. Here, if we have 2 times 3 squared, okay, that's one way to look at it is that's 6 squared, that's 36, but it is also 4, not 4 squared. Try to get my eraser here. There it is. Okay, so 2 squared is 4 times 9, which is 3 squared. My pen is rebelling here, times 9, also equals 36. Okay, so aside from the flashing around on the board here, we do see that the rule holds. Okay. All right, the last point I want to make is kind of ending with the same, but a different version of basically the same warning that I ended the examples video in the last session. A very easy mistake to make. Okay, so let's use my mistake color. Just a general warning here that x plus y to the nth power does not generally equal x to the nth power plus y to the nth power. I don't know why people want to think that it does. I do it. Everybody does it. It's a hard thing to get over. You can just start going really fast, and you can think that there's a distributive law here, and there's not. So just emphasizing that no big deal if you make this mistake. I hope you can just find the mistake quickly if you do make it. But again, let's just convince ourselves that it is in fact a mistake by using some numbers here. So if we have 2 plus 5 squared, okay, that is equal to 7 squared, that's 49, and that is not equal to 2 squared plus 5 squared, which is 4 plus 25, 29. These are not the same. Okay, so those are the rules of exponents. You've got some quiz problems and some more practice problems to use them with. So have fun, and I'll see you in the next lesson.